Hello there. I'd like to start by discussing the efficiency of an algorithm. How good is it at doing what it does? We talked about, well, I've talked about one sorting algorithm, bubble sort. Hopefully, you've read up about another one, quicksort. I'd like to go back to bubble sort. You may remember that if we've got six numbers that we want to order, we do it through a series of passes. The first pass would take five comparisons, and at the end of that, we know that either the largest or the smallest, whichever order we're doing, is in the right place. So the next pass would take four, and the next would take three, and the next would take two, and the next would take one. So for six items, it takes 9, 12, 14, 15 comparisons. This, of course, is worst case scenario, isn't it? We know that bubble sort, you do have the potential for it to stop early if any one of these passes involves zero swaps. So whenever you consider the efficiency of an algorithm, you've really got to think about the worst case scenario. This is the worst case scenario for six items. Now, that was quite easy to work out, but for something like, 20 items, 20 numbers in a list, we're looking at this sum, aren't we? All the way down to that. So how many comparisons is that? And ultimately, what about n items? How many comparisons would you need for n items? Well, this allows us to introduce something which you'll come up against when you look at sequences, and that is finding the sum of a linear or an arithmetic sequence. So this is an arithmetic sequence where you start with 19 and your difference is -1 each time, and there are 19 terms. How can we add that up quickly? Well, it's quite a nice little party trick, actually. I don't know if you've ever come across it before. What you do is you imagine that same sum written out again in reverse. And so what we've got now is 2 times my sum. So if I add up all of these numbers, I'd need to divide by 2 to get the actual sum of the original sequence. But the reason I've done that is that if you take the pairs of numbers, they all add up to 20. Okay, so I'm going to pause at this point. Your task is to tell me, for 6 items, it took 15 comparisons. What's the worst case scenario for 20 items? Can you use what we've done there to tell me how many comparisons you would need? And then can you extrapolate that for n items? Pause and have a go. Okay, so you've got each pair of numbers adds up to 20, and there are 19 pairs, so it's 20 times 19, but that's the sequence twice, so you have to divide that by 2, giving you 190. So what about n items? Well, this is what the sum would look like for n items, and that's the same sum written upside down, so this time each pair of numbers adds up to n. There are n minus 1 passes in the worst case scenario, and you have to divide that by 2. So the number of comparisons you need to make, well, we could write it in a number of ways. We could write it like that, or we could write it like that. But the key thing is it's an expression with n squared as the most complicated power in it. And so what that means is bubble sort is a quadratic order algorithm. So the order of the algorithm is the amount of work it has to do for n items. So you can have linear order, which is order n. That's where the formula for how much work it has to do just is in terms of n. Quadratic order, n squared, which is what we've got here, cubic order, n cubed. You can get square root, and if you look up the order of quicksort, it's a particularly complicated one involving logs, and we haven't done logs yet, but never mind. So what does it mean that you've got a quadratic order? Well, it's a little bit like the relationship between scale factor and area. So let's say that you have some algorithm that will sort or do something to 100 items, and the time it takes to do that is 4 seconds. All right. And let's say this is an n squared, a quadratic order algorithm. So if you double the amount of items, then the amount of time increases by that squared. So it would take 16 seconds. If it was a linear algorithm, order n, then doubling the amount of items would just double the amount of time. If it was a cubic order algorithm, doubling the amount of items would increase the time by 2 cubed, by 8, much in the same way that scale factor and volume are related. So so that gives the opportunity for questions on the efficiency and order of algorithms. Let's have a look at a couple of those. So, sorry, I don't know why I can't get this to focus. I shall try again. Mind you, I've printed it from that dodgy PDF I downloaded on myself, maybe that's why. So a particular list searching algorithm has linear order, and 500 values take 0.036 seconds. How long would it take to search this? So what's the multiplier there? Well, it's happy days, isn't it? We're back to good old after divided by before to work out the multiplier. So is that 2.5? I think so. And it's a linear algorithm, so that means the time will also increase by 2.5. So we've got 0.036 times 2.5. So that's 0.09 seconds. Okay, and what about bubble sort? So here we go. We've got, given that it takes a computer, so bubble sort is quadratic order, so it takes a computer 0.2 seconds to sort 1600 numbers. How long will it take to sort that? So again, after divided by before, something to do with 3, isn't it? 480,000 divided by 1600 is 300. So the number of items has increased by 300. It's quadratic order, so that means the time increases by 300 squared, 0.2 times 300 squared gives you 18,000 seconds. And of course that's not good, is it? So, comment on the suitability of the bubble sort algorithm sorting large data sets. It's not very good. And quicksort is certainly more efficient. Okay, so I'm going to give you some practice for that once we've just covered this next bit, because the two things tend to be sort of rolled together. So we've done sorting algorithms. The next sort of algorithm we have to deal with are referred to as bin packing algorithms, although I like to think of them as cross-channel ferry loading algorithms or cutting lengths of wood algorithms. Let me explain what I mean. Back in the day, on the at the War Memorial Crossroads roundabout in Ilfracombe, there was a hardware shop on the corner there. I think it's now where the Caribbean takeaway place is based. Although it never seems to be open, so I don't know what's going on. But anyway, it used to be a hardware store, and it was the sort of place you could go in and you could say, right, I want 3 meters of wood this particular size, and the guy would go down the steps to his little storeroom, and he'd pull out a length of wood and cut it to length, and you'd only pay for what you want. Unsurprisingly, it didn't survive the modern sort of DIY shop and Amazon type craze, but there we go. It was a great place to visit. So why are algorithms needed for that sort of situation? Well, let's just say that I run a hardware shop and I sell wood in 4 metre lengths. And in a day, 3 people come in and ask for these lengths of wood. If I add those lengths together, I get less than 8 metres. Less than 8 metres. 7.7 metres. So really, I should be able to, provide people with these bits of wood and only use 2 of my 4 metre lengths. Or can I? Can you see the problem I have? Well, the first person comes in and here's my 4 metre length. And they buy 3.5 metres. So there you go, they take 3.5 metres. So I'm left with half a metre of wood. The next person comes in and they want 0.6 metres. So this isn't enough, so I have to break into another length. So I have to cut 0.6 off there, which leaves me with 3.4 metres. Next person comes in and they want 3.6 metres, so I haven't got enough. So I have to break into a third length of wood, which would leave me with. And this is a problem. I'm left with 2 quite short offcuts and a length here which I'd probably be able to sell, but I'm unlikely to be able to sell exactly all of it. And it's the same problem as a cross-channel ferry. A cross-channel ferry, here it is, has got lanes that you park your cars in, and your first lorry comes and goes up to there, and then your second lorry comes and goes up to there, and your third lorry comes and goes up to there, but your fourth lorry won't fit in there, so your fourth lorry has to go in here, and it's you can't run a business if you've got empty space on your cross-channel ferry, because you're going to lose money. So this is why we need algorithms to do this sort of thing for me. Now, actually, there's no way an algorithm would have improved that situation. So I picked a rather extreme situation, but we're going to look at some examples where an algorithm is helpful. And there are 3 algorithms which are very, very straightforward. First fit decreasing, and full bin packing. So let's have a look at let's have a look at those in order, starting with first fit. Okay, so they're called bin packing because you've got this sort of concept of loading boxes into like containers. A bin is like a container. If effectively here we've said we've got containers which are 2 metres long, and you've got boxes of these lengths to fit into those containers. So let's draw me some containers which are 2 metres long. Now the first thing we can do is we can work out our sort of theoretical minimum number of bins or number of containers, which is referred to as a lower bound. So if I've done this for you already, if I add that up, those lengths up, I get 8.5. So I know I'm going to need at least 5 bins, because you couldn't fit 8.5 into 4 bins, even without any wastage. So I'm going to need at least that, maybe even more, because of the issues that I discussed with my wood cutting example. So how does it work? So let's assume that the boxes are arriving from here in this order, and when this one arrives, I don't know what else is going to come. That's the key thing. That's like cars driving up at the cross-channel ferry. You don't know what's going to come after them. So I've got 2 metres here. Can we fit these into these 5 bins? We're going to use first fit. So first fit just says take a length and fit it in the first available box. So there we go, that fits in that one, that's good. And then you do the same for the others. 0.7, yeah, that's fine, that fits in that one as well. 0.8, yep, that's all good. I can fit that one in there as well. That takes me up to 1.8 meters in that one, so I can't fit this one. This one will have to fit in that bin. Now, I mustn't forget, I've still got a bit of space in this one, but there we go. Right, so you have a go and see if you can fit those in. Okay, so the 0.8 and the 1 fitted in that one, all looking good so far. I've then got 1.1, which fits in that one. Another 1.1, so I can't fit in that one, have to put it in that one. 1.2 won't go in any variable, so that's another fresh box. And then the 1.5, yeah, that's not going to work, is it? So I've got to use 6 boxes, 6 containers, 6 bins in order to accommodate these. And you can see how this is in many ways a worst case scenario because they're getting longer as they go. But first fit can be problematic like that because we don't know what is to come. We don't know what is to come. So here's a second question for you to try. Use the first fit algorithm to pack the following items into bins of size 20. So I think I'm going to perhaps get away from the drawing bit. So I'm just going to sort of go, right, I've got a 20, a 20, a 20, a 20, a 20. A is 8, so A can go in there. B is 7, so B can go in there. Right, go on then, see if you can finish that one off and state the number of bins used and the amount of wasted space. Pause and have a go. Okay, so it's A and B fit in there, C fits in there, D won't fit in there, so it goes in there. But when I get to E, you're always starting at the top and sort of working your way down. So E wouldn't fit in there, but it would fit in there. F wouldn't fit in there, wouldn't fit in there, but would fit in there. But G would fit in there. So when you come to a new item in the list, you're always working all the way down to see if it fits in. And that's something to remember when you come to the efficiency. And particularly remembering that efficiency is sort of a worst case scenario. So anyway, so that's first fit. Very simple. So first fit decreasing, I'm sort of hoping you can probably predict how that works. Let's have a look at an example. Okay, so first fit decreasing we can only use if we know everything that we're going to be asked to pack in advance. So you can't use first fit decreasing if you are running a shop and people are just turning up saying, I want this much wood, I want that much wood. You can only do it if you've got a list of everything you need to pack in advance. And all it does, unsurprisingly, as the name suggests, is before you do it, you put everything in decreasing order. So it's the opposite to that worst case scenario we had in our first fit example. So here we go. We pack H in that one. C won't fit in that one, so it goes in that one. I put them in order. D and F, doesn't matter which way around I put it. Won't fit in that one, won't fit in that one, but they'll both fit in that one. A won't fit, won't fit, won't fit, goes in there. So go on, pause the video and see if you can finish that one off. Okay, so it's much more efficient, uses one less bin, and we've only got 6 units which are wasted. Again, can't be used in every situation because you need to know everything you're going to be asked to pack in advance. And but if you do have that luxury, it's a much more efficient way of going about it than to use first fit. Let's look at the third and final sort. Okay, so full bin packing is common sense. What you do before you do anything else, and again, it's like first fit decreasing, you need to have a view of everything that you're going to be asked to pack first, is you firstly work out how many full bins can you get. And then the things you're left with, you pack using first fit or maybe first fit decreasing. So if we have a look at this example here, we've got to pack these items into bins of size 25. So, straight away I'm looking for combinations that add up to 25. So A, B and C add up to 25. So that's straight away one full bin. A, B and C. And I have got, where else have I got? 12 and 13. That's another 25, so that's an E and an I in there. And I've got D and J. That's another full bin. And I've got, I think that's it, isn't it? That's it. Right, so what's left? I've got F, G, H and K. So I'm just going to use first fit for those. So all these bins are full, so nothing I can do there. So F is going to go in there, and G will fit in there, but H will not. And F and G add up to 21, so K won't fit in that, so K goes in that one there. So I've managed to squeeze them into 5 bins by firstly using the full bin algorithm. I love, often algorithms sort of, they make something which is very common sensey sound very important, the full bin algorithm. And then I just used first fit for the remaining items. Is my solution optimal? Well, let's circle right back to the thing we did at the beginning where we worked out the lower bound. So if I add all my lengths together, I get 111. So I know they wouldn't have fitted, even with 0 space, they wouldn't have fitted in 4 bins. So the lower bound is 5. So yes, my solution is optimal. I've managed to do it in 5 bins. So we've looked at first fit decreasing, and full bin algorithms. Okay, so the theory and examples I've just been through are on pages 22 to 29 in the PDF version of the textbook, or 16 to 23 in the Active Teach version of the textbook. You should all have access to that. These page numbers are from the Active Teach textbook, but you're a smart kid, you can work out how to convert it if you've only got the PDF. Packing questions, the book does it in the opposite order to me. Order of the algorithm questions. This is an interesting one. I put a star by it because the first part, it gets you to consider the order of first fit. And remember, when you do that, you've got to consider the worst case scenario. All right. And then the mixed exercise at the end of this, we sort of got to the end of this little mini chapter on algorithms. There's a good selection of questions there. I'm not saying go away and do them all, but the E questions are always the ones to focus on. So that'll take us through to next week, because obviously I'm not going to see you on Thursday, but we will pick up with the next chapter next week. Hope you are all okay.